For the T1 ANC project, I want to just quickly show you where we're up to in terms of the acoustic system, electroacoustic system. So we have made up some samples. It's using the current housing and driver, and we just modified this rear cap, and there's a board in there with a MEMS microphone on it for feed forward. It's not the same microphone they were using for voice before. Hopefully, ideally, it's a slightly better performing microphone, and the setup is adjusted so it's got a better acoustic response. So the unit's built, and inside the one wire connects directly to the driver, the other one to the microphone. So it's 3 wires. There's power, ground, and signal. It's a MEMS microphone, so we supply power to it. I've added a microphone preamplifier. It's got about 5 times gain, and that provide the power and signal. So we run the signal from that to feed forward microphone into the tester with this. We've got a header on the side here for 2 channels of feed forward microphone. We'll plug those in. This one, actually, I'll make sure I get left and rights correct first. That's the right, and that's the right. That's good. And left here, should be left, yes, it's the left. We'll plug those in. So the purpose of this, of course, is to measure the ideal, what calls it the ideal feed forward filter, and decide what we're going to do to realize that filter. I have 2 samples, slightly different tuning setup, and one of the questions, of course, is given the limitations of a digital system in terms of latency, etc., which version is it easier to realize in terms of the feed forward filter? So we'll plug it in, we'll make a measurement, and we'll have a look at what we've got so far. Into the couplers, I've got speakers for external noise on the left and right side. There's an amplifier here driving those, and we get the signal out of the back of the tester. And here we go. Okay, we just got to rubbish for the frequency response, because I better plug that in too, and we'll do that again. So you'll hear I'm using a chirp signal for both the frequency response and the external noise. Our first plot is the frequency response driver to air microphone. We'll call it air microphone, measurement microphone, another name. So we get this kind of frequency response. It's not really a great response. It's going to sound quite cloudy and muddy. We can adjust it by EQ to get something nice, I guess. But again, in the project for the moment, we want to try and keep those parts unmodified, keep it as simple as possible, use what they've got. If we discover that we cannot realize that filter for whatever reason, we could look into modifying that, but it's best if we can avoid doing that for the moment. Everything stays as it is. I do notice, I've had a look at a couple of samples, and there's quite a bit of variability in the higher frequency range from these drivers, so it's not a super high tolerance driver. Hopefully that is, we can deal with that. It doesn't put us outside the limits of what's acceptable. So we get frequency response, of course, we need that. I'll come back to this in a second. The next one is the spectrums. So we've got 4 curves: feed forward microphone, right and left, and then air microphone, right and left. And that's just measuring the signal straight out of the speaker. We put in a chirp and we get a spectrum from that. So clearly you have this fairly typical, it's essentially a passive noise isolation effect, where at high frequency the attenuation for the air compared to the feed-forward microphone is much greater than at low frequency. That's pretty typical. What you'll see for a lot of modeling of feed-forward systems is they take these noise, call it a speaker to feed-forward mic and speaker to air, to compute the ideal filter. I don't like to do that because this data on its own doesn't really have any meaning. It's kind of the frequency, say the feed-forward filter is kind of the frequency response of the speakers or all the surroundings, but it doesn't carry a lot of meaning. It's not really relevant directly if we had a perfect speaker in a perfect environment and with a perfect feed-forward mic, we'd get a flat line. But that's not really helpful when that's never really the case. Okay, in this setup, we don't have an anechoic room or reverberation chamber. We're just set up in a convenient location to put the camera on and things like that. But what we can do is compute directly the transfer function from feed-forward microphone to ear microphone. So we don't need to look at these spectrums directly. And that's this one. That's what we call the housing response. It's more meaningful. You can see directly this is the behavior of sound coming from feed-forward microphone to ear microphone as it passes through and around the housing. So we get a more sensible curve. Yes, it's going to roll off. Not a huge passive isolation. You could say it's like a passive isolation, although the sensitivities of the two microphone, feed-forward and ear microphone, are not the same. So it could shift up and down. Like I said, it's got 5 times gain on that microphone. So, but we do see we get this kind of characteristic. We'd look at this directly when trying to set up a feed-forward system to see. We want to get something pretty nice and even here. Okay, the headphone response there. For housing response spectrums, then we take that housing response and the driver frequency response, divide them, and compute the ideal filter, and there it is. And so this is our ideal filter function. It's very even, nothing crazy going on in this the lower region. Once you get up to high frequencies, of course, you will start to see a lot of resonance behavior. And so, okay, our phase is in the, up towards plus 150. So this brighter line is the magnitude, the slightly dimmer lines are the phase, magnitude and phase. So up at 150, of course, that we would actually reverse those speaker connections, I guess, for a system. So the filter function we want would actually subtract 180. So whatever is it, minus 30-ish or something like that. So we'll shift that, we'll phase shift that 180 degrees, but the shape of the curve is the same. Here we're just wrapping past 180. We could unwrap it, but you can just imagine that, when you have this kind of a dip, the phase has a corresponding peak. So this is the ideal filter for this setup. I had a play with it with an analog board, and mapping this part of the curve is quite okay, but you do run into problems when you have these kind of notch functions. It's very hard to get an analog filter, a realizable, a practical filter that will follow that curve nicely. So that's one unit. Well, I'll actually okay, we'll store that. One of the other questions is, what about the position of the speakers and reflections, and how much of an influence is that going to have? So I stored that curve. What we'll do is we'll just set it running continuously, and we'll move the speakers around and have a play around, and we'll see how much of an influence that has. And that's going to answer part of the question of how should we set things up, and how much of an effect will that have. So I'll just press and hold. That will just cycle continuously. You might not hear me when the sweep is going. Okay, so what happens if we, say, move the speakers so we're firing, reflecting off the back wall? And so we're looking at the ideal filter. It's getting computed each time, and essentially there's no change at all. I'll just disconnect one side completely. If we look closely in the high frequency, of course, we get huge differences. But in our real target range, there's virtually no difference. So the orange curve is this side. It's getting a lot more strange behavior from reflections and so on than this side. But the underlying function remains more or less the same. Of course, as we spin it around, we get a lot noisier and things like that, and we get strange comb filter effects. I'll connect this one again. get right in the back of it. Okay, we'll stop that. So the upshot of that is we regardless of where we put the speakers, we get a very similar function, ideal filter, at least up to 1 kilohertz, and that's what you'd expect. It's all wavelength related. Once you get past that, the angle of incidence of the sound becomes really important. But we'd aggregate a lot of those measurements to find out essentially a median curve, and that'll give us a good representation of what we need to do to cancel noise that may be coming from any side. That's great. That's one unit there. We've got another one. I still have that stored. That's great. I'll remove that one. I'll change to the other unit that I've set up slightly differently. Basically, I want to see if we can do something about that notch. So when we have the notch, the phase climbs very rapidly, and it's right around the point where we do want to be tapering the filter off, and we want to avoid having a lot of noise addition. So we don't want our filter to be, we don't want to have a gain where we don't want it, essentially. So let's see if we can get our left and rights correct. That's the right, that's the left. So here's an alternative setup. And so part of the question is, see, what I don't understand is in terms of a digital filter, how do these characteristics, in terms of a transfer function, how do we account for the effects of what is basically latency is going to be the key factor? And what kind of a setup is going to be most easily realizable in a digital system as opposed to an analog system where you have essentially zero latency, so you're not concerned about that factor. You're only concerned about trying to keep the function as simple as possible so you can make a kind of a decent practical filter. If you have really sharp cues, let's say in a analog system, it's really unmanageable. The tiny component tolerances start to have a huge influence, and so on and so on, and you don't have that issue. So I'm plugged in, here we go. Bit of a big click there for some reason. Okay, so I'm not sure how well this comes out on the video, but this unit, we got rid of the notch. In fact, what's happened is we've gone to a little bit of a peak instead, and from the viewpoint of an analog setup, or I guess a digital setup in the same way, if we roll off our amplitude here, we're not going to be adding noise. We'll lose cancellation, but at least we won't be adding noise. So we could run, perhaps up to around 1 kilohertz as we start to deviate from that target phase function. Frequency response is fairly similar overall. There is some differences, but as I mentioned, the drivers are not that, don't have a very high tolerance. So, okay, we can't do a hell of a lot about that unless we dig into driver and so on. We'd like to avoid it. We'd like to say we can come up with a filter function that's going to do the job across the range of drivers that we already have in the product or that the supplier already has. Otherwise, we're opening up quite a big challenge in terms of getting the driver dialed into a specific function. However, it is a possibility. Low frequency roll-off is not the greatest. Again, if we were able to play with the drive, we could probably tune that out, at least reshape it so that we're not rolling off quite as much. But again, that's just one of the parameters that we have. Housing response, so essentially we've converted the dip into a peak by modifying that rear housing behavior. And the assumption is that may make it easier to realize the filter. And of course, as I say, the spectrums, you look at it on its own, it doesn't really give you much information. So we'll look at the housing response. So I mean, for example, you have a little tweak here. I could fix that up because these have a vibration when they're sitting on the grommet. There is a resonance there. In practice, you won't really get that because it'll be held in the air in the pinner. We could, use a little bit of putty or something to settle those down, and that would maybe address that. In fact, let's try it and see. I'll just do it on one side. We'll just sort of kind of simulate the effect of having that partially secured. And we'll go again. So that would be the blue. Yeah, eliminated that wobble. But of course, if we sort of take a mean curve, we're not concerned about these sort of wobbles too much when we take a mean curve through the range of data that we get. We'd pretty much ignore those type of things anyway, so it's not worth taking too much effort to eliminate it from the measurement. We'll just account for it in the way that we calculate our filter. I do have an SD card in there, so what I'll do is store this data. Again, I would normally take a whole bunch of measurements, moving the speakers around and just see how it's influencing that range. We'll do that kind of offline separately. But essentially this one is let's say our current best guess. So the question is, if we go ahead and build up the mechanical parts like this, is that a reasonable filter function to work with? Of course, I always use it in terms of a transfer function. We can convert that to an impulse response. I'm just not that familiar with working with impulse responses or looking at that data and getting meaning out of it. In terms of a transfer function, I'm more familiar with a magnitude and phase thing. And so that is, more broadly speaking, of course, how does a latency influence a transfer function? That I don't have a good understanding of. So we'd like to find out those things. Then we can finalize what we're doing with the mechanical design and make a filter for it. The ideal scenario would be to have some kind of a development board with the digital chip on it, and we can solder on these wires, program a filter, and then actually measure the feed-forward cancellation and see what we're getting. And I think that's covered basically everything we want to say for now, so let us know what you think. Thank you.